Dear students, welcome to second B1S, second A1S and B1. I'm going to explain the topic theory of estimation. Theory of estimation, before giving the introduction, it is nothing but the sample should be drawn from a population. Based on the sample, the parameter theta can be estimated. So the definition is theory of estimation is the method of estimating unknown parameter on the basis of random sample drawn from a population with the density function f of x comma theta. Here theta is unknown parameter, so that we have to estimate the parameter theta on the basis of the sample. So in this theory we talk about estimator and estimator. Estimator nothing but a statistic which is a function of the sample values, very well. And numerical value of estimator is estimate. An estimator is denoted by Tn and the parameter is denoted by theta. So based on this there are two types of estimation. One is point estimation, and the point estimation is like that. The method of determining a single value for estimating parameter theta is called point estimation. Based on point estimation, we have the criteria of good estimator. So criteria of good estimator is the most important in this topic. Let us say the good estimator, which is nothing but the estimator which satisfy four criterion. One is unbiasedness, second is consistency, efficiency, and the fourth one is sufficiency. It is also called criteria of good estimator or simply good estimator. Now we study one by one very carefully. Number one, unbiasedness. Unbiasedness is the property which is the expected value of an estimator Tn, which is equal to the true value of the parameter. That is called unbiasedness, and that is expectation of Tn is equal to theta, or theta cap is equal to Tn. That is the expected value of Tn, which is equal to the true value of the parameter. It is called unbiasedness. That is, if expectation of Tn is equal to theta, then Tn is called unbiased estimator of parameter theta, and its property is called unbiasedness. We have so many examples and proved already, and theorems are there. Now I discuss consistency. This property in which estimated Tn is said to be consistent estimator of parameter theta and satisfying two conditions. One is limit n tends to infinity, probability of modulus of Tn minus theta greater than epsilon is equal to the epsilon is a small quantity, it is always positive. And the limit second one is limit n tends to infinity, probability of modulus of Tn less than or equal to epsilon, Tn minus theta less than or equal to epsilon is equal to 1. This called consistency. Then Tn is called consistent estimator of parameter theta. Now we move to the efficiency. Before that we define most efficient estimator. So among all estimator, there is just one whose variance is less than the others is called the most efficient estimator. Let us take two T1 and T2, two estimators with variances V of variance of T1 and variance of T2. If variance of T1 less than variance of T2, then T1 is called most efficient estimator, or variance of T1 by variance of T2 less than or equal to 1. Let us take T1 is the most efficient estimator, T2 is another estimator with variances V1 and V2. Now we define the efficiency of T2, which is denoted by E and defined as E is equal to V1 by V2. If E is equal to 1, then T2 is called most efficient estimator. So another definition of efficiency E is equal to minimum variance divided by variance of Tn. It is a very important concept, remember that one. Based on that we have a number of theorems. Now we move to the fourth one, sufficiency. An estimator Tn is said to be sufficient estimator of parameter theta if it contains all the information in the sample regarding the parameter, and its property is called sufficiency. That means the information should be contained in the sample regarding the parameter. Then it is called sufficient estimator. Now we go for based on sufficiency, we have two types of criteria. That before that defining we should define likelihood function of the sample. This is the likelihood function of the sample. We should first draw the samples like x1, x2, xn, which are nothing but random samples drawn from a population with the density function f of x comma theta. Your likelihood function of the sample is denoted by L of x comma theta or L, and defined like this. It is joint probability density function or probability mass functions. L is equal to probability of p of x1 into p of x2 into p of xn, or L is equal to f of x1 into f of x2 into, like that we had to multiply all this in the case of discrete, in the case of continuous. Based on that we have likelihood function. We have criteria 1, Fisher-Neyman criterion. First what we do, we should draw the sample from the population like x1, x2, xn, which are nothing but n random samples drawn from a population with the density function f of x comma theta. The likelihood function of the sample x1, x2, dot xn is denoted by L of x comma theta or simply L. Let us take t is a statistic and its probability density function is g of t comma theta. Then your Fisher-Neyman criterion is nothing but the necessary and sufficient condition of Fisher-Neyman criterion is that the likelihood function is split as the product of the function, like L is equal to g of t comma theta into h of x1 comma x2 comma xn, but which is independent of theta. Then t is called sufficient estimator. And we have criteria 2, it is Neyman factorization theorem. Similar way Fisher-Neyman, like we should draw the samples like x1, x2, xn from a population with the density function f of x comma theta. The likelihood function of the sample is nothing but L. Then let us take two functions k1 and k2. The necessary and sufficient condition that the L may be split as a product of two functions, that L is equal to k1 of t1 comma theta into k2 of x1 comma x2 comma xn, which is independent of theta. Then t is called sufficient estimator. This is one important concepts, Fisher-Neyman criterion and criteria of good estimator for examination point of view, very important. Then very important concept is method of estimation. We have two types of method of estimation, namely maximum likelihood estimation, method of moments. Now I discuss the method of maximum likelihood estimation. First what we do, we should draw the sample like x1, x2, xn from the population with the density function f of x comma theta. The likelihood function of the sample nothing but L, already defined. L is equal to p of x1 into p of x2 into p of xn, or L is equal to f of x1 into f of x2 into f of xn. And what is ML estimation? ML estimation is the procedure of maximizing the likelihood function L for estimating the parameter theta. That is maximizing means we have to differentiate. L should be maximized by satisfying the following equation: dou log L by dou theta is equal to 0, dou square log L by dou theta square less than or equal to 0. That means it is a negative. The above equations are called ML equation, and solving them we get estimated parameter. This method what we called ML estimation method. And the method of moments, the last one. Let us draw the samples, n rand samples x1, x2, xn with the density function from a population with the density function f of x comma theta. In this method, let us take the moments of population and sample. The moments of the population are denoted by mu r dash. That is mu r dash is equal to integral minus infinity to plus infinity x power r into f of x into dx. The moments of the sample are denoted by AR. AR is equal to summation r is equal to 1 to infinity xi power r by n. The method of moments is that equating the moments of the population and sample for estimating the parameter theta. That is mu r dash is equal to AR. Mu r dash is the equation, AR is equal to, this method is called method of moment. Thank you very much for listening this my class. Thank you very much.